Can you hear me? Yes. Thank you very much. Thank you for the invitation. Very happy to be here. I think it's one of the largest, if not the largest, conference in Schubert calculus, and the conference haven't even started yet. So it's good. It's a good thing to see that the subject is growing. So I'm gonna tell you about quantum K theory. So I have 3 lectures to talk about this, but my lecture is lecture D, coming after 4 other lectures. So really, my lecture is the 8th lecture. So maybe it's a good time to kind of pause and ask the easy question, which is, where are we and where are we going? Okay, so where are we? Well, for the moment, at least for today, we are here. So what we talked so far, we talked about the cohomology, just the cohomology of a flag manifold or of a Grassmannian. We talked about, yesterday we heard about the equivariant cohomology. Today we're gonna hear about K theory. And in the next 2 days, we're gonna hear about an extra theory, which is called the quantum cohomology, quantum K theory. So these extra Q theories, they're called K theory or cohomology, but they are not really cohomology theories in the usual sense, in the sense that they don't satisfy functoriality properties. So they are called quantum cohomology or quantum K theories for historical reasons, but they are not really cohomology theories. So we're gonna see. But today we're gonna talk about an honest cohomology theory, this K theory, and there are various ways to actually go from one theory to another. So if you want to go from K theory to just usual cohomology, you have to take the so-called top term. I have here a little map called GR. That GR stands for associated graded. So what we have here, it's going to be a filtered ring. So it's a ring with a filtration. And if you take the associated graded of this ring, or equivalently, if you take the top term of this ring, then you're going to recover a calculation in the usual cohomology theory. If you go to the quantum side, then we're adding an extra parameter Q. If you make the Q is equal to 0, you recover the non-quantum side. And you have this big happy diagram where essentially the parallel lines are the same type of maps. You can see the GER here, you can see the GER here. So if you want to go from quantum K theory to quantum cohomology, you get the same GER. And then you can see the GER here if you want to go to, sorry for this. So if you want to go from equivariant quantum K theory to equivariant quantum cohomology, again, this is a filtered algebra, and you just have to take the GER, so there's some top term, and you're going to get the equivariant quantum cohomology. And this is, I like this, so this is a way too early example in this lecture, right? So hopefully by the end of the 3 lectures, you're going to have an idea of at least how to get this calculation. O321 times O21. So what are the O's? The O's are the Grothendieck classes. These are the Schubert classes in K theory. Now I'm using this funny circle product, which is going to be the quantum K product, and I'm multiplying those 2 classes together. So as you know from the usual Schubert calculus, the first thing you should do when you multiply classes together, in order to see what you should expect on the right-hand side, you should count codimensions. In other words, you should count the number of boxes in the partition. So partition 3 to 1 has 6 boxes, right? This is the 3 to 1. And partition 2-1 has 3 boxes, so 6 plus 3 is equal to 9. So now you're looking in the right-hand side, and you're looking at terms and their degrees. The degree of Q here is equal to 6. So the first term has degree 9, right? So there is a Q here, which has degree 6, plus 3, so 6 plus 3 is equal to 9. So this term has degree 9, which is the same thing as the degree of the left-hand side. So this is going to be a term in the quantum cohomology. It has the same degree as the left-hand side. The next term has degree 10, 6 plus, oh no, actually still degree 9. So still this is a term in quantum cohomology. The term after has degree 10, so 6 plus 4 is 10. This is going to be a term in quantum K theory. So you see the quantum K theory has terms of degree more than the degree of the left-hand side. Okay? So this is going to be a quantum K theory term. If you just want to recover the usual cohomology, then you just make all the q's equal to 0. If you make all the q's equal to 0, there is only one term that survives, and you look at the degree of that. That degree is equal to 9. So that's actually a term in the usual cohomology. If you multiply 3 to 1 by 2, 1 in the usual Schubert calculus, in the usual cohomology, you get 0333. Okay? So this calculation is very easily obtained using, for example, Anders' equivariant Schubert calculator, which is available there. Also, I wrote lecture notes and also which are available on my website. So that's the address. So you can also look at the slides there and the homework there. So you don't have to write things down. Things will be available there. Okay, so for a while now, I'm going to spend some time defining what this thing is. And I'm going to focus on the general facts about K-theory. And then I'm going to switch to the flag manifold. So what is K-theory? So for simplicity, I'm going to get the complex projective manifold. So everything is going to be smooth. I don't have to consider smooth, but it's easier if you want to explain things. So K-theory is a ring. It's a ring which is generated by symbols of vector bundles over your variety. So you have symbols of vector bundles, and then you have some relations. The relations are given by two symbols. So one symbol, the symbol E, is equal to the symbol of F plus the symbol of G, whenever you have a short exact sequence of vector bundles over the variety X. So you just have vector bundles over these Whitney relations, and then the addition, the multiplication just comes from the addition and multiplication of vector bundles. The addition of vector bundles means taking direct sums, and the multiplication of vector bundles means taking tensor product. So it's very easy to define K-theory. There is a pairing. All these rings come with a pairing, and the pairing it's very important in everything that we do. It has to do with a degree, in cohomology, in K-theory, and so on. So this thing comes with a pairing. The pairing in this case is given by the Schiff Euler characteristic. So if you want to pair the class of the vector bundle E by the class of the vector bundle F, what you do is you just multiply the two things together and you integrate, as Alan put it, right? So what does integration mean in K-theory? I'm going to explain this a little bit later, but for now I'm just going to say, oops, okay. There, good. So the integration in K-theory just means Schiff Euler characteristic, so is the alternating sum of the dimensions of the cohomology groups with coefficients in this tensor product. So that's the pairing in K-theory. Now, we're talking about vector bundles, but really we want to get about, and to talk about Schubert classes. Now, the Schubert classes are associated to Schubert varieties. Schubert varieties they don't really have like a vector bundle description. So what you can associate to a Schubert variety, or in general to any subvariety of a smooth variety, is you can associate the structure sheaf. Now, the structure sheaf is not going to be a vector bundle, it's going to be just a coherent sheaf. And then the point is that if you have a manifold, so if you have a smooth variety, so if Y inside X, it's a closed subvariety, but X is smooth, then it turns out that the structure sheaf of Y has a finite resolution by vector bundles. Because you have a finite resolution by vector bundles, then you can regard the class of OY as an alternating sum of the vector bundles arising in the resolution. Of course, this resolution is inexplicit. I'm not telling you how you get it. And there are going to be better ways to understand what this class is. But for now, what I'm trying to say here is that I can associate a class in K-theory to any subvariety of a smooth manifold. Okay? So this gives a class in K-theory, and more generally, if you have a coherent sheaf. I didn't define what coherent sheaf is, just take it for granted. I'm not going to explain what it is. So if you have a coherent sheaf, then you get such a resolution, so you get a class of that sheaf inside the K-theory, and these are called the Grothendieck classes in the literature. And as I said, we don't really have to assume that X is smooth, but if you don't do that, you lose a little bit. So first of all, if you don't say that X is smooth, you always have a Grothendieck ring of vector bundles, because you can always add and multiply vector bundles, but you only have a Grothendieck group of coherent sheaves. Okay? And the relations in the coherent sheaves are given by the short exact sequences of coherent sheaves. And if X is smooth, then the Grothendieck ring is equal to the Grothendieck group, just because of the resolution. Okay, so by now we know what is K-theory. Again, it's just vector bundles modulo the Whitney relations. So let's do some examples. So let's work out the K-theory of a point. Yes? Yes. You don't have a multiplication in that situation. You don't have a multiplication in that situation. So no. So okay. So that is up to this point is when X is smooth. So when X is smooth, I can do that, right? Because I have a resolution by finally many vector bundles. If the resolution is infinite, then I don't know how to express the class of a coherent sheaf as an alternating sum, because I have to make sense of the infinite resolution. Yeah. In some sense, it's a point. Yes, that's right. Yes. So the resolutions are finite whenever X is smooth. If X is not smooth, you cannot guarantee. All right, so let's discuss about the K-theory of a point. So what are the vector bundles over a point? Anyone knows? I'm hearing whispers which have the right vibe. So maybe just let's make the whispers louder. Vector spaces. So vector bundle over a point is just a vector space. Okay. Now, of course, vector spaces, maybe I want finite dimensional. So I have a finite dimensional vector space. Now, vector spaces, of course, they have a basis, right? So they have a basis, so they're going to split into line bundles, okay? So what is the only invariant which determines a vector space is the rank, right? So every time when I have a vector space, the class in K-theory is completely determined by its rank. So this tells you that the K-theory of a point is going to be isomorphic to Z. Of course, you also can take formal inverses of vector spaces. Okay? So the K-theory of a point is Z. I'm not going to say what is the K-theory of P1 for now, but I'm going to discuss some elements in it. Can you give me an element in the K-theory of P1, which is not identity? The tautological, very good, thank you. So indeed, on P1, we have the tautological sequence. So Dave mentioned about these tautological sequences last time. So this is the tautological sequence on P1. I'm going to write it in this way. So this is a sequence of vector bundles over P1. The fiber of O of minus 1 over a line over a point in P1, corresponds to a line in C2. So the fiber over the point, say, x0, y0 in P1 is really the line in C2 corresponding to that point. So that's why this is it's a line bundle, right? It has rank 1. Okay. So this is so these are all elements. So O of minus 1, C2 as well, C2 over O of minus 1, these are all elements in the K-theory of P1. We know from the Whitney relations that we have the class of O of minus 1 plus the class of C2 over O of minus 1 is equal to the class of C2, which you can think of it as 1 plus 1. C plus C. Okay, so you have, this is your first relation in K-theory. We're going to see a bit later on that this Whitney relation actually give a complete set of relations. So there is an extra relation here coming from the determinants. The determinant of, so it's the product. The product of O, the determinant of O of minus 1 times the determinant of C2 over O of minus 1 is the determinant of C2. And those give a complete set of relations for the K-theory of P1. So these are your first examples. And in fact, in my homework, you have to play a lot with the K-theory of Pn. So that's my goal for these lectures. If you understand K-theory and hopefully quantum K-theory of Pn, it's great. It's already the quantum K-theory, it's complicated for Pn. Okay, so this is a bit, so this is nice. I mean, we have some very small examples, but still it's a bit inexplicit. How do you really do multiplication? As I said, if you want to do multiplications, yeah, you can easily do it for vector bundles, but what do you do if you have like two subvarieties? How do you multiply subvarieties? In principle, I have to take the structure shift of a subvariety, take a resolution by vector bundle, and then like tensor vector bundles after that. Well, that's complicated. So I don't want to do that. Therefore, I'm going to invoke this following, the following theorem. It's a theorem that makes precise what actually happens in Schubert calculus. Now, the theorem has lots of technical conditions. What I would ask you to focus on is on this statement here. That the class, so if you have a smooth subvariety, if you have a smooth a non-singular variety X, and if you have Y and Z closed subvarieties, then the class of Y times the class of Z is the class of the intersection. This is the key fact here. And of course, there is a price that you need to pay. This cannot be true in general. This is true in the presence, well, in the absence of bad singularities. So if the singularities are good, for example, if we have this Wien singularity, which are Cohen-Macaulay, this Wien property, so if the varieties Y and Z are have expected codimension, and if they are Cohen-Macaulay, then this thing happens. So this is going to allow us to actually calculate products in the presence of nice singularities and in the presence of transversality. Okay? So as an examples of varieties which are Cohen-Macaulay, so any smooth variety is Cohen-Macaulay, any Schubert variety is Cohen-Macaulay, but this is a serious theorem. If you intersect, if you put Cohen-Macaulay varieties in general position, if you intersect, then they're going to be Cohen-Macaulay. Later on, we're going to see the modular space of stable maps is going to be Cohen-Macaulay. And you also have that this Cohen-Macaulay property is preserved by smooth pullbacks. The smooth pullbacks arise, for example, when you project from one flag variety to the next. So here's an example. So let's try to work out what's the multiplication in the K-theory of Pn. So, well, maybe I'm going to take P2, maybe P3. So let's take K-theory of P3. So let's say that I want to multiply the class of a point with the class of a point. What do you expect that to be? Well, I have 2 points, right? So remember, the K-theory class, like the cohomology class, is invariant under translations. We're not working equivariantly here. I'm allowed to move my points so that they are in general position. If the points are in general position, then what happens? Indeed, if the points they are in general position, then the intersection of 2 points is empty. And then I can use the previous theorem, right? So the previous theorem tells me that OY times OZ is O of Y intersected to Z. Okay, how about if I put a hyperplane in P3 and I multiply with another hyperplane? What do I get? We get the class of a line. And now you can guess what's the K-theory of Pn out of this, right? Of course, there is something which I didn't prove, but we're going to talk about this later, which is the fact that the K-theory of Pn is actually generated. It's a free module which is generated by the class of the point, line, plane, three-dimensional plane, and so on. So all these linear spaces. But out of this, and using the previous theorem, you can actually do multiplications of nice classes. And we're going to see later on that these nice classes actually generate everything else. So in fact, you understand what is the K-theory of Pn. All right, so we discussed about the definition. We discussed about like how you calculate using these transversality properties, just some basic functoriality properties. So as I said, K-theory is a cohomology theory. So being a cohomology theory, it has to be equipped with push-forwards, pull-backs. There is a pairing that we discussed. So what are these? Well, first of all, K-theory has a kind of like a cohomology version and a homology version, depending on whether you consider vector bundles or coherent sheaves. And the cohomology and the homology version is a module over the cohomology. So the coherent sheaf version is a module over the vector bundle version, right? So this is what the first bullet here is saying, okay? So it's very similar to the cohomology, homology version of this. And then we have pullbacks and push forwards. So how do you define this? Well, whenever you have a morphism, as long as it's a morphism, then you can actually pull back vector bundles. So that gives you a pullback from, if you have a morphism from X to Y, that gives you a pullback from the K-theory of Y to the K-theory of X just by pulling back. But of course, if you're interested in intersection theory, then maybe you want to pull back not a vector bundle, but maybe you want to pull back the structure sheaf of a variety. Then you need some additional conditions. So it turns out that if F is flat, which I will not define, flatness is a very nice condition which among other things, preserves codimension. So if F is a flat morphism and Z of X, Z inside X is a subvariety, then the pullback of the structure sheaf of Z is just the class of the inverse image of Z. Okay, so you can do pullbacks. How about push forwards? So push forwards are much more complicated now. So if you have a proper map between two varieties, so properness is another algebraic property which is not easy to define, but you can think topologically is the preimage of a compact is compact. So let's just say that this is what proper means. So if you have a proper map, then you get a proper push forward between the K-theory of X and the K-theory of Y. And the proper push forward of the class of F is given by the alternating sum of the higher direct images. Now the higher direct images encode the cohomology, so the ith higher direct image encodes the ith sheaf cohomology of F restricted to a fiber. So if you look at the stock of the higher direct image of F over some point Y, essentially what you have to look at, the ith cohomology, sheaf cohomology of F restricted to the fiber over that Y. Okay. This sum is finite because the cohomology vanishes beyond the dimension of the fiber. So and then you have the usual projection formula. So the usual package of a cohomology. So you have pullbacks, you have push forwards, and you have the projection formula that tells you that the push forward of the pullback tensor F is just this E. So you kind of like cancel the push forward and the pullback, and then here you have to push forward this F. Okay. So the integration is kind of like it's a particular case of a push forward. The integration just means push forward to a point. And now remember that in order to define push forwards, you need proper maps. So the map from X to a point needs to be proper. And the definition, so that means that X itself has to be proper. This is the definition for X to be proper. It means that the structure map from X to the point is proper. So X has to be proper, and if that's the case, then the push forward of a structure sheaf is by definition is the sum of the higher direct images. But remember, the higher direct images are encoded in the cohomology of the fiber. And here, because we're pushing forward to a point, there is just one fiber, which is X itself. So this is going to be just the alternating sum of the dimension of the sheaf cohomology groups, also known as the sheaf Euler characteristic. So in K-theory, the push forward to a point and also the pairing encode sheaf Euler characteristics of appropriate objects. If you're talking about vector bundles, it's going to be the sheaf characteristic of the vector bundle. If you're talking about the coherent sheaf, it's going to be that. Okay? Yes? Yeah, so the higher direct, for the higher direct image, you really should think about the cohomology of the fiber. So if you have a map from X to Y, maybe I'm gonna, yeah. In fact, maybe I'm gonna put it this way. So if you have a map from X to Y, and then you look at a little point here, right? I'm gonna say something incorrect for the experts, but you know. So they are looking at this thing, right? So this is just the fiber over that Y0. And now you're looking, let's say that you're interested in the higher direct image of the push forward of some coherent sheaf F, right? So this is going to be some coherent sheaf which is supported on Y, okay? So how do I understand this sheaf? Well, I understand this sheaf by understanding its stalks. So now I'm interested in understanding the stalk at Y0. So the stalk at Y0 is some particular group. And that group, you should think of it as the ith cohomology group, because this is the ith direct image of the fiber over Y0 with coefficients in F restricted to that fiber. So now I'm cornered there, but you have to restrict F. So the restriction of F to that fiber, it's again some coherent sheaf. And then you have to look at the cohomology of that. I mean, I guess the easiest thing is if I just push forward to a point, I'm going to push forward O of 1 to a point from P1. So let me see. I think I have I have some extra. Okay, let me do it at the end. I think I have some extra blank pages here. Yes. Okay. So let's say that I go from P1, and if I have a point, right? So this is the structure sheaf, right? And then let's say that I'm interested in pushing forward O of 1. The class of O of 1, okay? So P1 is proper. It's a compact, it's a projective variety, therefore it's proper. So proper and projective, okay, let's just say they are the same. Let's just say, okay? So this is gonna be, so by definition, this is gonna be the alternating sum of the cohomologies. So it's gonna be -1 to the 0 dimension of H0 of P1 O of 1 minus dimension of H1. Bless you. H1 O of 1. So now you need to know sheaf cohomology of O of 1s. H0, so you're looking at the global sections of O of 1. So the dimension is equal to 2. We're looking at O of 1 has, it's just linear forms into parameters. And then O of 1 doesn't have higher cohomology. So this is 2 minus 0. So this is equal to 2. So in this case, the fiber is just everything, and the restriction of O of 1 to the fiber is just O of 1 on that P1. So that's kind of like, in some sense, the simplest thing, and you might have more complicated things. For example, when you go from one flag variety to another, you can get Borel-Weilbot in this way. It's global sections. Yes. So in general, H0 of Pn of O of 1, these are linear forms. So linear because it's O of 1. So linear has to do with a 1. It's linear forms. In how many variables? Well, in this Pn is really Cn plus 1 minus 0 divided by C star. So I have n plus 1 variables, right? This is Pn. It has n plus 1 coordinates. So it's linear forms in n plus 1 variables. So this is, the dimension of it is just n plus 1 with the basis x0, x1, all the way to xn. I would have to, yeah, I would have to use, for example, check cohomology to see why H1 is equal to 0. Yeah. So this is, yeah, the actual calculation of cohomology, yeah, this is part of the cohomology of Pn, cohomology of these bundles O of D on Pn. One proof uses check cohomology, and you'll have to look in, I think it's chapter 3 in Harshort. So. Yes, yeah, this is this O of 1, it's an ample. It comes from an ample divisor, so yeah, the higher cohomology of these ample ones is 0. And then there is their duality and so on. So if I have an anti-ample, then I can transform it into something which is ample. It's okay. So for flag varieties, Frank explained that line bundles are given by weights. And then you have to look at the dominant weights, anti-dominant weights, and each weight determines a line bundle. And then you have to look at the cohomology of the line bundle. And then you have the Borel-Weilbart theorem that tells you what is the cohomology of the line bundle. So if you have an ample line bundle, it has only zeroth cohomology, only has sections, but no higher cohomology. And then in general, you have to do a certain procedure to see which cohomology exists. So there's a full story out there about the Borel-Weilbart and how this is related to this. In some, yeah, so I can transform this. So Borel-Weilbart is usually for the full flag varieties, but of course I can pull back this O of 1 onto the full flag FLN. And in this case, it's gonna give me, so I can do, this is 1 and plus 1. I can do FLN plus 1. This is the full flag variety in Pn. Okay, I can do O of 1 here. So this one is gonna give me the determinant, this is Pn. It's actually S1. So this FLN plus 1 has a tautological sequence. Okay. Yeah. What I'm trying to say here is that the cohomology on Pn, if you want to write it in those terms, you can do it. And I have to identify for you what is the line bundle. And there is, again, some translation that needs to be done. I can tell you what is the line bundle. It's going to be the dual of that S1. Yes, it's going to be the dual of the S1, which is the tautological subbundle of rank 1. So I can transform the cohomology of Pn into some cohomology calculation on FLN, and then I can apply the Borel-Weilbart to calculate there if I want to. Borel-Weilbart. Borel-Weilbart. Okay. All right. Yes. So if you take FLN and if you take some line bundle associated to a weight lambda, and again, there is something that you need to do. For a weight lambda, there is a line bundle associated to it. Then the Borel-Weilbart will tell you what are the cohomology groups of this. So this will be equal to something. If the line bundle is ample, then the higher cohomology vanishes, you only get sections. If the line bundle is not ample, then you have to do a certain procedure, and then some higher cohomology, not usually, always, there is cohomology only in 1 degree, but you have to find which one is it. So I think this is a good thing for the students. So Alex is asking the questions, but maybe some students should ask. We're good? Oh, okay. You're getting to the point here. Right. Why do people care about such things? Well, we've seen Schur function in the very first lecture here. So the Schur function arises, of course. So these are representations. So this FLN can be written as GLN or maybe SLN in this case. I want to write it as SLN mod B. Okay? So these are representations of SLN. And all the representations of SLN arise geometrically in this way as cohomologies of line bundles on flag varieties. And okay, so the first question is to describe the cohomology of SLN, and the second question is to realize those. The first question is to understand what is the representation theory of SLN, and the second question is to understand how those representations arise from cohomology of line bundles. And then the Schur function arises as, so I may be off here. So the Schur function is the character of the, I didn't explain what the character is, but I was about to. So the Schur function itself arises as the character of the cohomology of FLN for a particular line bundle. You have to take dominant weights here. It's going to be, probably I'm going to be wrong with the conventions, but I'm going to ignore that. Okay? All right. Yeah, for P1 you have to take n is equal to 2. And then I have to take H0 of FL2. And then I have to take O of 1. And I have to take the dual of this, and I have to take the character. And so I'm going to get x1 plus x2 if I interpret this correctly. This is the character associated to a representation. I have to put the weights there and so on. So yeah, so we care about the worldwide mod because it gives us a geometric way to understand characters of reducible representations of complex semi-simple Lie groups. In this case, the complex semi-simple Lie group in this case is just SLN, and the character of the flag variety associated to it gives us Schur functions. And there is something going on here. I have to tell you what is x1 and x2 in terms of the characters of that representation. But you can see at least the 2. The 2 comes up because you just evaluate the Schur function at 1. So if you make x1 is equal to 1 and x2 is equal to 1, you get 2. The 2 was the rank of that O of 1. All right, so let me say a little bit about the Chern character. Okay, so the Chern character. The Chern character, it's kind of like coming from representation theory. If you're going to apply the Chern character to a representation, you're going to get the character of that representation. So, okay, so let's say that you have a manifold. Then the Chern character is just a map. In fact, it's a ring homomorphism from the K-theory to cohomology. It's defined in the following way. So if you take a line bundle, you have to exponentiate its Chern class. So if you exponentiate this Chern class, this sum here looks to be infinite, but in fact it's not infinite because this sum is going to vanish beyond the dimension of the variety. These operators act as 0 at the power n, which is bigger than the dimension of the variety. Okay? So, and in general, we heard from Dave about the splitting principle yesterday. So if you don't have a line bundle, but if you have a general vector bundle, then you can assume by the splitting principle that the vector bundle splits as a sum of line bundles. And the splitting is, and these line bundles have some chain roots x1 up to xr. And then the Chern character, it's multiplicative. So, oh wait, I just wrote something. So the Chern character is multiplicative, but this is wrong. So this is a plus here. So the Chern character of L1 plus L2 plus dot is going to be the Chern character of L1 plus the Chern character of L2, and so on. So in this way, you can actually calculate the Chern character of any vector bundle. But we've seen before that we're interested not necessarily in vector bundles, but in the structure shift of subvarieties. So what can we say about characters of structure shifts of subvarieties OZ? Well, it turns out that if you take the Chern character of that, the initial term that you get in cohomology is just the fundamental class of Z. And then you have higher order terms in cohomology. So, so this is, it's something interesting that goes on here. So the Chern character for smooth varieties is actually an isomorphism. So the K theory is isomorphic to cohomology. So you may ask, then why do we care about K theory? Don't we know already about cohomology? Why do we have to introduce a new theory here? Because this is an isomorphism. So this is an isomorphism, but it's not a graded isomorphism. It does not respect the grading. So there were two questions. I'll take Oliver first. Oh, I wrote CH of OZ. Yes. I'm going to get to rings with basis also, but I want to say, yes, I'm going to get to rings with basis also. And of course, it has to do with that, right? Because we're interested in rings which have a basis, and when you multiply two elements, you want to preserve the grading. The Chern character does not preserve the grading, and in fact, if you look in the homework, I'm asking you to actually calculate the Chern characters of some Schubert varieties in Pn, and then see what happens, okay? So although K theory and cohomology are actually isomorphic, the grading is not preserved, the structure constants are not preserved. All right, so the Chern character of O of 1, so let's just calculate that very quickly. So this is CH of OPN of 1. So by definition, this is the exponential of the first Chern class of O of 1. So this is going to be equal to 1, because it's an exponential, right? You just write the Taylor series. It's 1 plus the first Chern class of O of 1 plus the first Chern class of O of 1 squared divided by 2 factorial plus the first Chern class of O of 1 cubed divided by 3 factorial and so on. So now I have to tell you, of course, what is the first Chern class of O of 1. So this is going to be just the class of the hyperplane. I think maybe you have seen this in yesterday's lecture. So this is just the class of the hyperplane. This is the class of the hyperplane squared divided by 2 factorial. This is the class of the hyperplane cube divided by 3 factorial and so on. Now, what is the class of the hyperplane squared in the cohomology of Pn? Yes? Well, it's Pn, so it's codimension 2. So it would be if this would be P3, it would be exactly aligned, right? So this is I'm going to call this Pn minus 2 here, right? Divided by 2 factorial, and then it's Pn minus 3 divided by 3 factorial and so on, right? These are fundamental classes. So you can see that the Chern character does not preserve degrees. In fact, it starts, the initial degree is 0 in cohomology. All right, so one more general thing. The Hirzebruch lambda y class. So the Hirzebruch lambda y class, it's a useful tool, which you should think of it as the total Chern class of a vector bundle. It comes with some additional parameter, which has also geometric interpretation, but I'm not going to get into that. So if you have a vector bundle over a variety, the Hirzebruch lambda y class of E is just a formal sum, 1 plus y times the class of E, y squared wedge 2 of E, y cubed wedge cube of E, and so on. So of course, you go up to the top rank of the bundle E. This class is multiplicative in exact sequences in the sense that lambda y of E1, if you have a sequence E1 into E2 into E3 goes to 0, then lambda y of E1 times lambda y of E3 is equal to lambda y of E2. Okay? And I'm not going to get to, maybe I should skip this part. I'll just very quickly say that if you make y equals minus 1, then this is related to the so-called K-theoretic Chern class. Okay? I'm not going to get into that. You can look in the slides and we can discuss maybe after. that lambda minus 1 class of the dual, it's related to the self-intersection formula. So this was explained by Dave yesterday. If you have a vector bundle with a section, then the class of the section is actually arises as lambda minus 1 class of the dual of that bundle. So this Hirzebruch lambda y class actually arises in geometry in a very concrete way. And I'm just going to flash the Hirzebruch-Grothendieck-Riemann rock, and I'm going to put it in bold, friendly faces. This is the Hirzebruch-Riemann rock. I'm not going to define anything. So what is this? Maybe this is related to Alex's question from the beginning. The Hirzebruch-Grothendieck-Riemann rock tells you how you calculate the Euler characteristic of a vector bundle in cohomological terms. So on the left-hand side, you have a K-theoretic calculation, which is just the Schiff cohomology of E. On the right-hand side, you have some terms, the character of E, which is a cohomological quantity, and the thought class of the tangent bundle of X, which I'm not defining. It's again some type of cohomological quantity. If you multiply those two cohomology classes, and if you integrate in cohomology, then you get this Euler characteristic. You can recover, for example, the Borel-Bott out of this description. All right, so this is it with generalities. Any questions about the generalities? Now I'm switching to the flag business. You do this equivariant. So the character, so the Euler characteristic should be interpreted equivariantly, which is the character of the representation. Okay. All right. So okay. So flag manifolds. So there were several conventions about flag manifolds. I don't know on which side I am. I guess I'm on the side which writes X upper W's for things of codimension that has to do with that W. So in these talks, in all my talks, I'm going to look at the partial flag manifolds, and I'm going to refer to them as G mod P. So whenever you hear me saying G mod P, then you should just think partial flag manifolds. And then there are two special cases of these partial flag manifolds, one of them being the Grassmannian. In that case, P is a maximal parabolic subgroup. Yeah, this keeps, I don't know why. Okay, so the Grassmannian, it's a G mod P where P is a maximal parabolic, and then you have also the full flag manifold, which is a G mod B, where B is the Borel, let's say, is the Borel subgroup of upper triangular matrices. So this description came up in the very last talk by Frank on Tuesday, I believe. So associated to this data, you can define certain combinatorial objects and some such as the Weil group. In this case, the Weil group is the symmetric group. And whenever you have a parabolic which contains this Borel group, you can also define a subgroup of those which is generated by those simple reflections which are contained in the parabolic. And then you look at W upper P, which is the set of minimal length representatives for the cosets of W modulo WP. So as examples, if you take the flag variety to be G mod B, then the Weil group of B is just trivial. So then the W upper B, so the minimal length representatives for W over W lower B, are just all permutations. They are permutations in Sn. And if you take the Grassmannian, then the Weil group associated to that P is all simple reflections except the simple reflection which corresponds to this K. So that one is omitted. And in that case, we've seen that the minimal length representatives are in bijections to partitions. Partitions included in the K times n minus K rectangle. So you can write something like this here. And formally, that means this is a sequence of integers, which is weakly decreasing, non-negative integers, and the first part has to be less or equal than n minus K. And we're going to also use this notation of W check. So this notation comes from like Poincaré duality. So what you do is you take the longest permutation in Sn, which is just this n minus 1, dot 1. And then this W check is just the minimal length representative for W0W in W upper P. Okay? So this W checks will always index Poincare dual classes. All right, so let me just mention, so we discussed about flag manifolds, but we want to talk about K-theory of flag manifolds. And we've seen some classes in the K-theory of P1. Those classes came from the tautological sequence. Similar tautological sequences exist for any partial flag manifold. So for example, if you work on the Grassmannian, you have a tautological sequence of this form. 0 goes to S, goes to Cn, goes to Q, goes to 0. So again, these are all bundles over the Grassmannian. So this sequence is tautological in the sense that if you take an element in the Grassmannian V, then the fiber of this S over V is equal to V. Okay? So the fiber over a point in the Grassmannian is exactly the vector space corresponding to that point. Similarly, similar to O of -1. And Q here, of course, so this is just looking at essentially this exact sequence over each point. So Q has fibers Cn over V. So this is kind of bundleizing the short exact sequence of vector spaces, which is 0 goes to V, goes to Cn, goes to Cn over V. So this is the tautological sequence in the Grassmannian. All these are vector bundles, so they give you classes in K-theory. And we're going to look at these classes later on. We're going to see that these classes actually generate the full K-theory of the Grassmannian. For FLN, for the full flag variety, you have a more complicated tautological sequence, which comes from the flags. So you have 0 goes to S1, included in S2, Sn -1, Cn, and then you're beginning to write quotients. So this is Cn over S1 and so on. So everything happens over FLN. And you can guess what is the fiber of Si. So Si has rank I. The fiber of that Si is over a point, over a complete flag with ith component Vi. It's exactly that Vi. This is why this is called a tautological sequence. Again, we're going to look at the classes associated to these vector bundles. In fact, we're going to look at the quotients of them, which are going to be line bundles, S2 over S1, S3 over S2, and so on. So these are some examples of classes, interesting classes, in the K-theory of flag manifolds, which do not come from Schubert varieties directly. So these are just classes of vector bundles. But, of course, we also have Schubert varieties. And so we've seen this before. So every time when you fix a flag, then you can define a Schubert variety corresponding to that flag. And you've seen this definition, so I'm really going very fast over it. This is the Schubert variety corresponding to a partition lambda. And then there is also an opposite Schubert variety, which is written with x lower lambda. And the conventions are set up in such a way that the dimension of x lower lambda is the codimension of x upper lambda is the number of boxes in the partition lambda. So we've seen this maybe with different conventions, but we've seen this before. In group theoretic terms, they are closures of Schubert cells. So if you work in this G mod P, and if you work with representatives in W upper P, then you have lower and upper Schubert varieties, which are obtained as closures of the Borel orbits on the flag variety. You can take the B orbit closure, and you can take B minus orbit closure, and then they're going to give you opposite Schubert varieties. And it's just a matter of conventions on how you index them. So what is new in K-theory is that Schubert classes are not enough if you want to understand well the theory. You also need these so-called boundary classes. So what is a boundary class? A boundary class, it's a difference between the Schubert variety, and which is a closure of B orbit, and the B orbit itself. So it's written here, this is the closure of the orbit minus the B orbit itself. This is a B minus orbit here. So these are codimension 1 subvarieties of the flag varieties. One can prove that These are actually Cohen-Macaulay. And then what you look at this, what you do with this is you actually consider the structure sheaves associated to these classes. And we call these the ideal sheaves. So, oh, I think I just made a mistake here. This should be, yeah. This is, I'm going to write this in this way. I'm going to write this OXW minus partial XW, right? This is fine. So these are going to be the ideal sheaves. I'm looking at the ideal sheaves of these subvarieties inside the flag variety. Okay, so these are coherent sheaves. So they give me classes in K-theory. So we're going to see how these classes come up. Just a matter of convention, I'm using lower, upper, and so on. It doesn't matter if you work non-equivariantly. The O lower classes are O upper classes, provided that you change to the Poincaré dual Val group element. Similarly for the ideal sheaves. The I lower classes are equal to the I upper classes, provided that you change to the Poincaré dual sheaf. So it's not so important that like how we look, but occasionally geometrically we need to use both. Okay, so one thing for the Grassmannian, and I actually want to say it. So what happens for the Grassmannian? You have a very nice thing. I'm just going to make the statement. So if you have a Schubert variety, let's call it X upper lambda, and you're looking at the boundary of that Schubert variety. Okay, so this is just the Schubert variety minus the sum. So what happens here is that this, you can take the Grassmannian and via the Plücker embedding, which you've seen before, this embeds into a projective space, is the wedge K of Cn. This projective space comes with a line bundle, which is O of 1. And you can call this embedding I, and you can look at the pullback of this line bundle from Pn. Okay, so this is going to be some line bundle on the Grassmannian. That O of 1 has some section, and it turns out that you can actually take a section, so an element in the zeroth cohomology of that pullback, and it turns out that if you choose the section carefully, then this boundary, it's exactly the zero locus of this section, even scheme theoretically. So that may seem okay, so what, right? Well, actually that has nice consequences in terms of how you write down the class of the ideal sheaf. It turns out that if you write next exact sequence, which is this exact sequence, you take the Grassmannian, and this is minus the divisor of the Grassmannian, and this is O of ZS. So if you consider this exact sequence, and if you restrict it to the Schubert varieties, you're going to get that the ideal sheaf class corresponding to lambda is just the multiplication of O of minus 1 times the class of O of lambda. So the ideal sheaf has a very nice formula in terms of the Schubert classes. That's what I'm trying to say here. The ideal sheaf for a Grassmannian, this is not true in general, but for a Grassmannian, the ideal sheaf of lambda is just the Schubert class of lambda times the class of O of minus 1. O of minus 1 is just the dual of the class of O of 1 pulled back by the Plücker embedding. Okay. This is true for experts in more general situations, but it's not true for the full flag manifold. And now I guess I'm getting to the Schubert package and to Schubert calculus. So what is the Schubert package? So in the Schubert package, you start with the basis. In this case, we choose either the Schubert basis or you choose the ideal sheaf basis. So we have a basis. Once you know a basis, you need to know the dual of that basis with respect to the pairing. K-theory, it's a ring with a pairing. If you work with K-theory of the Grassmannian or of flag manifolds, then of course you want to know what's the dual of each class. It turns out that the ideal sheaves are duals to Schubert classes. This is why I had to introduce them. So the duals of the ideal, the Schubert classes are the ideal shifts and vice versa. So this is unlike the cohomology situation where the Schubert classes were self-dual. In K-theory, the classes are not self-dual. Yes? It's O of minus, yes, that's right. Not about, no. Yeah, you have to take the, yeah, it's a Weil divisor, right. You have to take the ideal shift of the boundary. Yeah, it's one, yeah, terminology, yes. It's O minus O of the boundary, right. So this is, so the ideal, it's the ideal of the boundary. Yeah, maybe I should call them just ideal shifts. Yes. So it's, so you have the exact sequence, it's O into O of x minus partial x into Ox into O of partial x. So this is the class I'm talking about. Is the ideal shift of the boundary. This is what I define here as well. Oh, yes, ideal shift of the boundary. I think I define it. Yeah. X is a, yeah, sure. X is a Schubert variety. Yes. I have X for me stands for X upper W. Yeah, so this is the ideal shift of the boundary of the Schubert variety. Okay, this is in general a Weil divisor. This is not a Cartier divisor. Okay. So what, I have minus 1 minute left, so maybe I'll just finish this slide. So we know what is the Schubert basis. We know what are the duals. So the duals of the Schubert classes are the ideal shift classes. These are the ideal shifts of the boundaries. Positivity. In Schubert calculus, you know you have a good basis when the structure constants that arise from multiplying these basis elements are positive in a certain sense. Here, we're multiplying two Schubert classes, two structure shifts, and we get some coefficients, C, U, V, W, and they satisfy a positivity property. So minus 1 to a particular power is the length of U plus the length of V minus the length of W. How do you get this power? Well, in cohomology, the right-hand side must have exactly the same degree as the left-hand side, right? So the left-hand side has degree length of U plus the length of V, and the right-hand side has degree length of W. In cohomology, the length of W is equal to the sum of the lengths of the left-hand side. But in K-theory, you may have higher lengths on the right. So these W's here may have higher lengths because you're going to higher codimension. The difference between the expected length and the length that you're getting gives you a sign. Minus 1 to that difference times the structure constants is positive. So that's the positivity in K-theory. This was initially observed by Anders, who actually proved the little Richardson rule for the Grassmannians, and was proved by Brion in full generality for any G mod P. And then I also want to say that the Whitney relation that we discussed give you a complete set of relations. Here I'm only stating the Whitney relations for the Grassmannians, but I can write Whitney relations for any partial flag manifold, at least in type A. So what you do here, you just multiply the lambda y class of S times the lambda y class of U. You get the lambda y class of Cn, which turns out to be just 1 plus y to the n, and you just identify the powers of y. So that will give you some relations between the wedges of S and the wedges of Q, and I'm claiming that if you transform this into a formal presentation, these are all the relations you're getting. Then, of course, you can ask what are the polynomial representatives of the Schubert classes, and I'm not even defining this, but you've seen them before. The Grothendieck polynomials turn out to be the representatives of the Schubert classes. So if you multiply two Grothendieck polynomials, maybe you've seen yesterday, you get some structure constants there, and those are exactly those that arise in the K-theory of the partial flag variety. Finally, functoriality. So, you know, flag manifolds are social objects. They like to talk to each other. So one way they talk to each other is you project from one flag variety to some other flag variety where you forget some of the steps. For example, you can project from the full flag variety to the Grassmannian, where you forget all the steps except the one for the Grassmannian. And I'm giving you what the formulas are. So if you push forward the class of a Schubert variety, you just obtain the class of the image of that Schubert variety. The statement is that set theoretically, the push forward of a Schubert is again Schubert, indexed by just the same value group element, but now you have to take it in a different quotient. And then this is also true in K-theory. So it's not only set theoretic, but also true in K-theory as classes using these higher direct images. And then the pullbacks are obtained just by pulling back. The pullback of a Schubert variety is again a Schubert variety, and the pullback of a Schubert class is the class of the pullback. Okay? So if you use these formulas, then you can actually reduce all the calculations in the Grassmannian to calculations on full flag varieties. So I'm way over time, so I'm going to stop here. Thank you.